Okay, welcome everybody. Let's get started. So today we're going to talk about EfficientML.ai lecture 10 about MCUNet and TinyML. So today's lecture, we are going to cover the following sections. So what is TinyML? What are the challenges of TinyML? And how to design those tiny neural networks? And what are the applications, including tiny vision, tiny audio, tiny time series, and also anomaly detection. So just give an overview of where we are so far. We talked about a lot of techniques to shrink, to compress neural networks, including brooding, quantization, distillation, neural architecture search. And now we want to combine these different efforts together and build some cool applications and really deploy them on small devices. So what is TinyML? Today's AI is pretty big. As we can show across the years, the model size measured in billions of parameters are growing super fast. But we need algorithms and hardware, new algorithm and hardware that is more efficient, okay? Efficient for inference, efficient for training, rather than taking a lot of resources for memory, for compute, but we can fit them in our pocket, fit them in our phones, right? And reduce the carbon footprint toward greener AI. So recently, the ChatGPT, the GPT-3, actually contains 175 billion parameters, right? It takes 355 years, GPU years, to train and costs more than $4 million, pretty expensive. And the AlphaGo beating LiSoDo took 1,920 CPUs and 280 GPUs, which costs $3,000 per game just to play one game. On the contrast, we hope deep learning can go tiny, right? So not only on the cloud, but also on the edge, where we no longer have to transmit our personal data, either the image or the text or the voice to the cloud, which may suffer from adversarial attacks, right? And privacy leaks, etc. But we want to keep everything local on the phones, and even on smaller devices, like IoT devices. For example, microcontrollers. And these microcontrollers are everywhere in our lives. There are billions of IoT devices around the world based on microcontrollers. And you can see across the years, the number of IoT devices are increasing, and they have very low cost, just a few dollars. So everybody can afford it, right? We can democratize AI to these low-cost edge devices. And also they are of low power, so we don't have to worry our battery gets drained, right? Running out of battery, or you go to spaceship, there's no Wi-Fi connection, there's also limited battery. You can run them in very low cost, in low power, even using renewable energy. That'll be super cool. And these TinyML application have a lot of usage across different aspects, like smart home, and control different appliances, in smart manufacturing, to do automatic defect detection, personalize the healthcare, adjust the dose according to different patients' symptom, and also precision agriculture. But it's not easy. TinyML is quite challenging. What makes it so challenging? The resource, primarily the memory resource. So for cloud AI, you can easily get, in this slide is showing 32 gigabytes of memory, but now you can easily get 80 gigabytes of memory, A100, H100 GPU, which has petabytes, terabytes, or even petabytes of data, of storage to store the weights on data. On mobile devices, like on our phones, you can easily get a couple of gigabytes of memory and hundreds of gigabytes of storage. That's plenty. But on those microcontrollers, the resource is tiny. You have a couple of hundred kilobytes of memory for the SRAM to hold those activations. And you have maybe just 1 megabyte of storage in the flash. right? And the flash is only sometimes read only, cannot write to it. Only the SRAM is writable. So the resource is very tiny. It's 4 to 5 orders of magnitude smaller compared with the cloud AI and also the mobile AI. So we need to reduce both the weights and also the activations so that we can fit these deep neural nets into TinyML devices. So compared with mobile AI, where we are constrained by the latency, and also we are constrained by the energy. Now we have a new constraint, the memory, right? Since these tiny devices has very little memory. A lot of the principles can actually be applied to large language model these days, since they are so big. Even one GPU cannot accommodate all the weights, like 175 billion parameters. If we don't quantize them in FP16, that's 340 gigabytes of memory. Well, a GPU has less than 200 gigabytes of memory. So same principle can also apply to large models. Okay, so let's dive deeper to understand the challenge, especially the memory challenge of TinyML. What is the bottleneck for the weight memory? What is the bottleneck for the activation memory? So this is an overview of convolution neural nets. You have a couple of conv layers, pooling layers, followed by FC layers in this case. For each layer, we have an input activation involved with a kernel, 3x3 kernel, and produce this output activation. And where do we need to store them? Okay, since we are constrained by the memory, let's dive deeper. Where are they stored? So input activation and output activation, we need to both read and write. Okay, we read the previous input, we write to the output of the next layer. So it has to be both readable and writable. So it consumes the SRAM, which is both readable and writable. As for static random access memory, SRAM. And for microcontrollers, they usually don't have any DRAM, only a couple of very little resources for flash. Okay, so it's read only. So only the weights. The weights is actually read only. If you don't do back propagation, if you don't do training, the weight can be stored in the flash. And the flash, different from SRAM, if you power off the device, the data in SRAM will be gone. Okay? The flash can hold the data. It's not volatile. Okay? But SRAM is volatile. If you power off the device, the data in the SRAM will be gone. You don't want the weight to be gone, so you have to store the weight in the flash. So these are some popular mobile microcontroller devices like Arduino Nano. This device has 256 kilobytes of SRAM, 1 megabyte of flash. This STM32 746, which we use, has 320 kilobytes of SRAM and 1 megabyte of flash. So very small resource. Okay, so the flash usage roughly equal to the model size because they are static. They have to be non-volatile. You need to hold the entire model. Okay, so the number of weights is constrained by the size of the flash. We are going to revisit this later part in the lecture. So the weight has to fit the flash, okay, since it's non-volatile. And the SRAM usage roughly equal to the input activation plus the output activation. Since they are read and read dynamically during the inference, and we care about the peak SRAM usage, which means the largest layer, okay, the size of the largest layer determines our peak memory usage. And weights are not counted here since they can be partially fetched. You can fetch them through compute unnecessary away. So what is the gap here? Okay, so this is comparing Res 50, MobileNet V2, MobileNet v2 Int8 version. Here is a 320 kilobyte of memory constraint that a microcontroller has, while Ryzen 50 peak SRAM usage 23 times larger. MobileNet v2 22 times larger. Quantization, we learned in the previous lecture, slightly reduce it by 4 times is very good, but still 5 times larger. Okay, so we are going to learn in this lecture how do we overcome this gap and be able to fit the model in the microcontroller while having similar accuracy as MobileNet v2. Okay. So what are the efforts? What are the prior efforts? Okay, so we learn about MobileNet v2, which is a very small model targeting mobile devices like mobile phones. But still, that's too big. And if you see the bottleneck, especially the activation bottleneck, it's very unfortunate that the activation didn't decrease, but actually increased by 80%. So it's very parameter efficient. So if you compare, here is the Ryzen 18. Here, this is the MobileNet v2, 0.75. Okay, the weight is reduced by more than 4 times. So that's pretty efficient. The weight is much smaller, so it takes less to communicate from the Apple Store to download the app, right? So that's pretty good. However, the peak activation didn't decrease, but increased. Okay, so that's a big problem we need to solve. So we are going to learn about MCUNet. Okay, not only reduce the weights by 6 times compared with Ryzen 18 with a similar accuracy, but also the peak activation is also reduced by 3.4x compared with MobileNet v2. Okay, so that's our goal. We have to balance both the number of parameters and also the peak activation. We have to fit both of them in the microcontroller. If you cannot fit any of them, you cannot fit the model. So let's go through formally how do we design these tiny neural networks, given the understanding of the challenges, given all the concept we learned so far. We'll introduce the MCUNet, the system and algorithm co-design. It was covered by MIT News a couple of years ago, which is very new. So what is system and algorithm co-design? We have a very large design space, right? We can either design the algorithm side by changing the neural network architecture, given a fixed library. For example, we learned Proxyless NAS, designing a customized, specialized model given the hardware, given the library. Right? There's other work focusing on assuming the model stays the same, but we want to develop new libraries like TVM. And what we find, the extreme efficiency comes from co-designing the neural architecture and also the inference engine. You need to co-design both directions so that you can exploit and explore a larger design space, including the neural architecture, propose efficient neural architecture, and also efficient compilers and runtime so that you can map the architecture on the inference engine. So the basic idea of MCUNet is system and algorithm co-design. In this lecture, we are going to cover the first part, which is TinyNAS, Tiny Neural Architecture Search, how to design automatically and optimize the model given the hardware resource constraints. And in the next lecture, we are going to cover the second part, the Tiny Engine, efficient compiler and runtime, how to optimize the inference engine. So let's start with TinyNAS, which has 2 stages. Okay, 2 stages for neural architecture NAS, for neural architecture search we covered before. Okay, this is a short recap. What is design automation for neural nets? What is the motivation for that? So remember, we covered in the previous lecture, rather than using a lot of engineers to hand design the model given different hardware constraints. Call it manual architecture design. Use a lot of human expertise, pretty expensive. We want to use machine learning to actually automatically search a good architecture that fits our demand. Neural architecture search. When we are doing the search, we talk about we need a good search space, right? So, like finding a friend in a forest, the forest is pretty large. We want to first narrow down the possible areas. For example, here or here, right? Narrow down the search space before we do the exploration. So the quality of the search space largely determines the performance of the search model. So the first stage of these two stages of TinyNAS is actually to search the search space and find a good subspace so that it feels promising rather than explore in the entire search space. We want to explore in a much smaller and constrained search space. So how do we find that search space? One approach, actually, you can reuse the prior search space for MobileNet, for example. However, the constraint for mobile device is quite a lot different from these tiny microcontrollers. They differ by a couple of orders of magnitude. So even the smallest subnetwork in the mobile search space still cannot fit the hardware due to the huge gap. Okay? So a mobile device has 4 gigabytes of memory versus a microcontroller has 320 kilobyte of memory. So even the smallest network in the search space still cannot fit the microcontroller. So what can we do? We can only design a new search space targeting IoT devices. And how do we do that? So we can scale down, we can scale the previous search space for MobileNet, right? Using a different resolution and different width multiplier. For example, the original search space typical for mobile devices, the resolution is 224 by 224, and the width is 1.0. That's pretty suitable for mobile phones. And we can scale them up for GPUs. Similarly, we can scale them down for microcontrollers. Then the question is, how large do we exactly to scale them down? Okay, they have different microcontrollers also has different memory budgets from 256 kilobytes all the way to 512 kilobytes. So the overall structure will be given a full search space. We want to add our memory and the storage constraint, and then produce an optimized search space, and then perform neural architecture search on top of it. So the optimized search space, including 2 design knobs, including the resolution and also the width multiplier. And after that, we narrowed it down, and then we search the kernel sizes, the expansion ratios, and also the number of blocks for each stage. So here is the algorithm for automated search space optimization. Okay, we want to analyze the flop distribution. Okay, we have seen this figure before, but let's dive deeper today. And analyze the flop distribution for satisfying models in each search space. So here, the x-axis is the number of flops in the search space, from 25 million flops to 65 million flops. The y-axis is the cumulative probability. Okay, and different curves corresponds to different search space. For example, the black search space, the width is 0.3, 30% weight, 30% width. The resolution is 160. And this red search space, width is larger, 0.5, resolution is smaller, 144. So in different search space, the flop is very different. For example, in the red search space, all the models has the flops more than 41 million flops. For instance, here is 41, and here is all the models has parameters larger than 41 million parameters. And 20% of the models, and here correspond to 80%. So one subtract 20 with 80%. So 20% of the models are larger than 50 million ops. Okay? Versus the black curve has much smaller number of flops. Here, all the models are larger than 28 million compared to 41 million. And here, this is 80%, 1 minus 80% is 20%. So 20% of the models has larger than 32 million flops, rather than here, it's 50 million flops. So we can see these two different design spaces can fit different amount of flops given the same memory budget. Since we learned that computation is cheap, memory is expensive, we want to maximize the amount of flops we can work on the same amount of memory footprint, or same amount of data movement. You fetch 1 byte of data, you want to do as much of compute by fetching one data, right? So of course, a good design space is showing that if a design space can achieve high flops, accommodate a lot of arithmetic operations under the same memory constraint, then it's likely to be a good design space. And that's indeed the case. For example, the red design space, the best accuracy we get is 78.7%. Well, for this black design space, the best accuracy we get is only 74%. Okay, so this is very helpful heuristic. Without having to train the model, we didn't even train the model, but we can just analyze the flops. Okay? Analyze the flops, we can accommodate given different design space to project the final accuracy. Okay, and let's see, given different constraints, let's analyze given different SRAM constraints, okay? And this is given different flash, size of the flash, ranging from 512 kilobytes all the way to 2 megabytes. So the x-axis is the flash, the y-axis is the SRAM, okay? From 190 kilobytes to 512 kilobytes, 192 kilobytes to 512 kilobytes. So we want to understand when the flash increases, but the SRAM size stay the same, what would happen for the width multiplier? And the first blue figure is for the width multiplier from 0.4 here to 0.9. And the second image is showing the resolution. And some of them is 112, some of them is 208. So when the flash increase same SRAM, what happens for the width multiplier? And the other question is, when SRAM increase, you have more SRAM in your microcontroller, same amount of flash, what happens to the width multiplier? And what happens to the resolution? I'll give you 1 minute to think about this question. And a hint is to consider these 3 points. First point, second point, third point. First point, second point, and third point. Okay, let's see the answer. So when the flash increase, but the SRAM stay the same, remember what gets stored in the flash, what gets stored in the SRAM. Right, exactly. So the flash stores the weight, the kernels, and SRAM stores the activations, right? So when the flash increase, meaning you can accommodate more weights, right? So you can have larger amount of channels. So that's why the width multiplier is increasing from 0.4 to 0.8. Okay? What about the resolution? Since we have the same SRAM, and the channels are getting larger, which means the resolution has to be smaller, so that the channel times the resolution square will be the same. Otherwise, you cannot hold it in the same amount of SRAM. Okay? So larger channel, smaller resolution. Okay? Larger channel, smaller resolution. What about when SRAM increase, but the flash stays the same? So SRAM stores your activations, right? But the flash stays the same. And so here, the resolution actually increased because you can hold more activations, right? You can hold more activations. But the flash stays the same, which means the weight actually stays the same. The flash stores the weight. The number of flash stays the same, so the width roughly stays the same across different channels, different columns of the blue figure. Okay? And since the SRAM gets larger, you can fit larger feature map, larger resolution. So across the column dimension here, you can see the resolution actually increased. So this figure gives you some intuition about the intertwining relationship between SRAM and flash, activation, weight, channel, and resolution. Any questions about this figure in general? Okay, good. Well, let's move on. So having figured out the design space, we can now perform the architecture search in this design space. Just like trying to find your friend in the big forest. Now you finally determine, okay, my friend is roughly in this area. Then I can focus on this area to search your friend in the forest. So here we use the once for all approach we learned in the previous lecture. Now we apply them to do some real stuff. So we train the super network, okay, this once for all network. We randomly sample different subnetworks, and we jointly fine-tune the subnetworks, and then repeat this process where the small child networks are nested in the larger ones. So we train only once. We can produce many different subnetworks. And by the way, the lab 3 is released today, the neural architecture search part. So make sure to visit our website at EfficientML.ai to download the neural architecture search lab. And the model searched by TinyNAS actually can better utilize the memory. So this is before, this is after. You can see the peak memory for different layer is very imbalanced for the hand-designed MobileNet v2. The difference between the max and average is 2.2 times. So the largest layer determined, the bottleneck is actually the largest layer. So you have to have at least this amount of memory so that you can hold this network. Well, the TinyNAS search model has a smaller gap between the max and average. It's more balanced versus there is a very big peak. So TinyNAS can design networks with more uniform peak memory distribution for each block, okay, allowing us to fit a larger model at the same amount of memory. So this is comparing the MCUNet with different prior work. MCUNet, this is MobileNet, proximate NAS, we learned before. This is our winning solution in 2029. Actually, we make it 2.4 times faster. So this is the latency. The lower, the better. And here is the visual wake words accuracy. The higher, the better. So MCUNet is faster. And also here is the memory. Peak SRAM measured in kilobytes. about 3.7 times smaller compared with this movement MV2. Okay, the green part is movement MV2. So let's revisit the problem of this imbalanced memory access, where the peak memory is actually the bottleneck, not the average. And to recap, the SRAM usage is dynamic. We care about the peak SRAM. So roughly, we can find there are two regions. Okay, the first region is layer 0, 1, 2, 3, 4. Okay, so this is memory consumption for each layer in this case, ranging from 500 to 1,400. So this is the memory usage across different layers. The first couple of layers is using a lot of memory, very high bars. And the later blocks, as you downsample, the resolution gets smaller and smaller. So the activation is actually getting smaller and smaller. And here is the 256 constraint of a microcontroller. Okay, so this is our memory constraint. And what happens here? You can see from stage 0 to stage 4, they are all above this 256 constraints of the microcontroller. But after layer 5, they are all below this memory constraint, which means after layer 5, it can fit. But before layer 5, especially layer 2, is actually 8 times larger compared with our constraint. So only the later blocks can fit. But the first couple of blocks has very high memory consumption. It cannot fit. So if we can reduce the memory usage of the initial 5 stages, then we can reduce the overall memory. And so how do we save the memory? So we can break the memory bottleneck by patch-based inference. So let's look at the original conventional approach. So here we have 2 layers. This is layer 1. This is layer 2. At each layer, we gather the whole input, produce the whole output, and then produce the whole output for the next layer. Every time you have to finish calculating the whole output of a particular layer, like layer 1, before you calculate layer 2. What is the alternative? So rather than calculating everything, now we just calculate 1/4 of the activation, and then we can directly go to the second layer. We just calculate just like eating a pizza. If the pizza is too large, you cannot eat it. Then you chop it, divide it into 4 pieces, and eat a smaller pizza. And here we have 4 smaller pizza. And finally, we have to hold the entire output, assuming after a couple of downsample layers, this becomes a smaller pizza. Okay, so this one has to be everything. We have to hold everything in the memory. But before that, for these larger activations, we can divide it into several patches. So we call that per patch inference, rather than this kind of per layer inference. And what is the upper bound of the memory saving in this case? How much times of memory can you save? Depends on the number of patches, right? So here we divide it into 4 patches. So the upper bound would be 4 times. If you divide it by 3, the upper bound would be 9 times. But it's the upper bound is not achievable because you have to you have to store all the activations in the next layer, the final layer in the memory. So let's see what happens after applying this patch-based inference. So by using the per layer inference, it keeps the memory, the peak memory is 1,372 kilobytes. But after applying per patch inference, it reduced to 172 kilobytes. It's a lot less. So it's pretty amazing that all these high bars, large memories, now suddenly gets much smaller, even smaller than 256 kilobyte of threshold of the microcontroller. It's pretty amazing. Finally, we can fit it. And now let's see the theoretical 4x saving for 2x2 patch and the 9 times saving for 3x3 patch. What is the actual achieved saving? So the highest bar corresponds to the per layer inference. Okay, 300 kilobytes in this case. And the middle part is per patch, about 2x2 patch. Okay, so 315 now becomes 113, roughly 3x saving, not 4x, since that's the theoretical limit. But if we use 3x3 patch, that becomes about 5 times, 4.9 times smaller, reduce it to only 64 kilobytes. Same observation for different network architectures, which is pretty good. But is there any drawback, any problem, any overhead using such kind of per patch based inference? Latency overhead. Where does the latency overhead come from? Sequential rather than patches, right? If the parallelism of the device is pretty big, now you limit the parallelism. But in microcontrollers, they usually have very low parallelism. You can issue 2 instructions per cycle. Usually on microcontrollers, that may not be the limitation. GPUs are ideal limitation. But overall direction is right. There's latency overhead. But where does the overhead come from? So if you think about just one layer, so this is just one layer output, this is the input. The convolution has a receptive field. If this 3x3 convolution, the output is 2x2, what is the effective receptive field? So here you have a 3x3 conv, destroy is 2, remove it by 2 pixels, so the receptive field is 5 by 5. So everything in this yellow region will impact the yellow region here. Everything in the blue region here will impact blue region here. They have no overlap at this point, but they have a 1 pixel overlap here. Repeated computation, redundant computation in the halo region. And even before that layer, the receptive field gets propagated. It gets larger, and there's a 3x3 overlap halo region. So it's not complete, divided independently, but they have the overlap. The yellow region and the blue region overlapped by 3x3, 9 pixels. Okay, so such overlap caused the computation overhead. And such spatial overlapping comes from the receptive field growth, leading to a larger computation overhead. And how much is the overhead? We measure that on model ME2 and find it's about 10% overhead. Okay? So everything an order of magnitude smaller can be ignored for first order approximation, but actually we can do optimization to actually remove that 10% overhead by redistribution. How do we do that? Since the reason for this overlap is due to the larger receptive field. Okay? The receptive field from 2x2 to 5x5, 7x7, you have a larger receptive field. What if we limit or reduce the receptive field? That will reduce the area of the halo, the overlap region, right? So actually, we can redistribute some layers. So here, the first couple of layers, we are using per patch based inference. And later layers, we are using the normal per layer inference. Since remember in the figure here, only the first couple of layers suffer from pretty big activation. Okay? But later, these late layers, they can fit the memory already. So we don't need to apply the per patch based inference in the later stage, but only in this early stage before here, we have to apply this per patch based inference. And since the receptive field is causing the memory overhead, let's reduce some of the receptive field. We can change this 3x3 convolution into 1x1 convolution. Okay, smaller kernel size means smaller receptive field. We can also remove one layer, remove one 3x3 layer to reduce the receptive field by 2. But the total receptive field need to remain the same, so we can compensate that by redistributing the receptive field from the first stage to this later stage. Look at here, we added one 3x3 convolution layer to compensate so that the final receptive field stays the same. So we use this network redistribution to reduce this overhead. And finally, the latency, the number of max here, the number of max using per patch based inference becomes the same as before. Although we changed the architecture, the receptive field didn't change. And we tested the accuracy after training, the ImageNet classification, object detection, their accuracy is very well maintained. All right, so finally, we can apply this per patch based inference into the search space and jointly search the neural architecture and inference scheduling methods. So the neural architecture includes the number of layers, number of channels, kernel size, resolution. Inference scheduling means whether we use per patch based scheduling and how many patches do we use, like 2x2 or 3x3. You can see there's diminishing return. How many layers do we use this per patch based inference, and also other knobs in TinyEngine we are going to cover in the next lecture. Okay, so putting everything together, we can further improve this visual wake words, right? Under only 32 kilobytes of memory. So what is visual wake word? Basically telling whether there's person or no person in the field. So this is the improvement across the years. So x-axis is the measured peak SRAM usage. The smaller, the better. Y-axis is the visual wake words, VWW, visual wake words accuracy. So this is our 2019 results. This is 2020 result. This is 2021 result. Every year we are pushing the frontier by 2 to 4 times smaller. Like from MCUNet, this is the version 1. And here is the version 2, MCUNet v2, which introduced this per patch based inference using 2x2 patch. We can save about 4x the memory consumption. Or using the same memory, 118 kilobyte, but achieve 4% better accuracy. And look at this model, only 30 kilobytes of SRAM, but achieving 90% top accuracy. And using per patch based inference, the peak SRAM at the same accuracy, 90% accuracy is reduced by 4x. And not only on the binary person versus no person classification, but MCUNet v2 also advanced classification detection to large scale, like on ImageNet level classification result. So this is the accuracy improvement of MCUNet v2 versus MCUNet under 256 kilobytes of SRAM versus 320 kilobytes of SRAM. Quite big improvement. Given the same memory, now we can fit a larger model, larger activation, so that the accuracy is higher. And this is MCUNet v2 plus CMSys, which is a inference library from ARM. And this is MCUNet v2. This is the object detection accuracy, also a quite big double-digit improvement from MCUNet v1 to MCUNet v2. So let's take a 5-minute break before we dive into details to dissect MCUNet v2. All right, welcome back. So let's continue to discuss, let's dissect the mobile MV2 architecture to understand some of the design principles and see this kind of automated design actually have lots of insights. For example, the kernel size in the per patch stage, which is this early stage where the resolution is pretty big, the activation is pretty large, so we have to use per patch based inference to fit it in the memory. Okay, the kernel size is actually chosen to be pretty small. That's a decision made by our neural architecture search algorithm to reduce the spatial overlapping. Okay, the smaller the overlap, the smaller the halo, the less overhead for compute, which makes a lot of sense. In the middle stage, the expansion ratio is actually small to reduce the peak memory, because here the downsample layer is not too many, so the resolution is relatively big. It's not as big as here, but it's much bigger than those later stage. So the expansion ratio in the middle stage is small to reduce peak memory. And the expansion ratio in the later layer is getting much larger, much wider here, because the resolution after a lot of downsample is already pretty small. So you can fit a much larger width. And also we find we can fit a larger input resolution. Okay, for those resolution sensitive data sets like visual wake words, make sure you have a larger resolution. So even a smaller person far away, you can still detect him or her. Versus our last generation MCUNet v1 can only support up to 128. Now we can support 160. Okay, so having learned about how to search, how to design tiny models, let's try to visit some to see what kind of applications can we build, including tiny vision, tiny audio, and also tiny time series, and also anomaly detection. So starting with the simplest, tiny image classification. So this is a demo from Google showing the microcontroller can do very simple classification between oranges, bananas, and apples. And here is the probability. Actually, this is super easy. You don't even need a neural network. You can just look at the colors, the RGB colors. So you can easily distinguish different fruits. But what gets more challenging is to expand it to large scale, right? On ImageNet level, real life applications. MCUNet can actually achieve that. More than 70% top accuracy. This is the level of MobileNet, where it used to require a mobile phone to do such tasks, but now you can fit into a couple of dollar microcontroller. First, to achieve more than 70% image accuracy of commercial microcontrollers, compared with prior work like MobileNet can only achieve 53%. Another application is by the way, there are different constraints of microcontrollers. Some of them has 256 kilobyte, some of them has 2 megabyte flash, some of them have 1 megabyte flash. It's very hard to design different models for different weights, for different constraints, right? But thanks to the advanced for all network, we can just train a single model, and then we can specialize according to the constraints for the activation, constraints for the weight, just training only once. We're going to explore such automated search using in our homework in lab 3, which is released today. Feel free to try it out. Another application is for image classification is visual wake words. So what is visual wake words? To detect if there is person or no person. If it's just background, we don't have to trigger the second pipeline stage, like recognizing who it is. We can just keep it idle. This might be a much larger model since it's more complicated to see who it is. But the first stage can be done in a very small model. Okay, if there is person, then the second stage, which is face recognition, will be triggered. Otherwise, we don't trigger that to preserve the battery, to save the privacy, etc. Here is a demo we shot in building 38 in the elevator. This is my postdoc. So we have this microcontroller right here as a light. If it is red, it's showing there is person. If this green is showing there's no person recognizing them on the microcontroller. And we also have a demo from our TA JPEG, and you can distribute the demo across everybody to take a look. You just place it in front of a person to see the lights. If it is a person in front of it, it'll be red. Otherwise, it should be in green. The microcontroller without a screen is the visual vehicle demo. We can also do a tiny object detection, okay, using this per patch-based inference. The challenge is that to do object detection, you really need a pretty high resolution. And high resolution means we need a larger activation. Larger activation means a high SRAM consumption, which is challenging. And resolution matters a lot for the accuracy. So here, from large resolution, if you shrink the resolution, the accuracy is going to degrade, not very much for ImageNet in the in the red and yellow curve. Well, actually, you should point the camera to someone and see the vertically. Just can you please tell them the direction? It's not horizontal, it should be vertical, remember. But if you can see for the detection to work, it's actually very sensitive to the resolution. If the actual resolution gets smaller, the accuracy drops very sharply here. So per patch-based inference is getting very helpful to maintain the accuracy. So here's a demo for object detection. This is face and mask detection. This is person detection. And you can see here the person comes, and here the mask is green. And then this has no mask, so it's red. This project was done during COVID, so we can tell from the demo is when the project was done. We have a lot of masks at that time in the lab. And what is the advantage of using such patch-based inference? Okay, so this is without using patch-based inference. This is with using patch-based inference. You can see this boy was missing, the detection was missing, but using patch-based inference, it can be detected. And here there's a missed prediction on the hand, but there is no missed prediction. Versus here, the man got lost with bounding box because the face was side face, and now we can detect it using MCUNet v2. Here is a missed prediction. Here is no missed prediction. So high resolution helps a lot. For patch-based method allows for larger input resolution, which helps a lot with the accuracy. We can even do on-device training, okay, to learn new tasks on the microcontroller. So here is a demo. We have two buttons on this microcontroller, a red button and a green button. We push the green button for the orange. We push the red button for the banana, and then do it a couple of times to give it a few labels. And here is doing the back propagation locally on the device, including the gradient, the activations, the weight. We have to fit everything in the microcontroller. And after a while, we can distinguish the banana versus the apple. Okay, we are going to learn such technique in the later part of this lecture when we talk about training. So that's tiny vision task. We can also apply it to tiny audio tasks. So audio is a very common application in our daily lives. Like we can do audio keyword spotting, like hey Alexa, okay Google, hey Siri, etc. For speech recognition, for noise cancellation. And actually we can turn this audio problem into a visual problem, because we can convert the speech signal, okay, like here, yes, into the 2D feature map. Okay? The x-axis is the time dimension, the vertical dimension is the frequency dimension, okay? And the strength indicates the power spectrum on different frequencies, so that we can do convolution on the 2D feature map. It's no longer one-dimensional, it actually becomes two-dimensional. So we can run those classification problem similar to an image recognition to understand the speech, whether it's yes, no, on, off, etc. So you can usually outperform the fully connected layer using convolutional layer, since there's the locality relationship between in time versus in frequency, adjacent time versus adjacent frequency. Usually the signal has relationships. So we want to capture those local relationships by convolution. And here we can see the false reject on CEM, the models is really better than the FC layers. And MCUNet can also improve the efficiency on speech command data set. We have a lot of speech command, and we want a low latency and high accuracy. So this is comparing MobileNavi2 Proximity NAS versus MCUNet, which is on the good frontier. And finally, we have tiny time series and anomaly detection, widely used in the factories, and also applied it to video surveillance in healthcare to prevent fraud, to detect abnormal products. So here we can see this is a normal capsule. This is an abnormal one. This is a normal nut. This is an abnormal nut. And we want to use this machine vision to detect those different anomalies, and also analyze very long videos to see something anomaly happen. But recently, with the advancement of large language model, especially the visual language model, there are alternatives to that. So we're going to cover this later in the lecture, but we want to give you a peek. So just put these two nuts and feed it to our visual language model called VLA. It has 7 billion parameters. It can do a lot of stuff. Here we ask it, the first image is normal. It's a normal nut. What is abnormal for the second image? And I can tell the second image is abnormal because it shows a nut with a hole in it. So it can generalize quite well, understand images and languages. So the technology is evolving pretty fast, just within 2 years. I made this slide roughly 2 years ago, and now a lot of changes in the technique with the advancement of large language model, which will be our focus for the second half of this lecture. So before large language model, how was this done? To detect the anomaly with autoencoders. Okay, so autoencoder is a very key technique. So given a input signal, it first passes through an encoder, okay, and projected into a low-dimensional code vector. So input may be of high dimension, like high-resolution image, but here it has a very low dimension, which is a abstraction of the input. Okay, and finally we pass it through train a decoder. The decoder takes this low-dimensional vector as input and try to reconstruct the output to be the same as the input. So that's the structure of an autoencoder to predict the input. Ideally, the x flash should be the same as x. And during the training, we try to minimize the reconstruction error. So this is the input, this is the reconstructed output, which was reconstructed into using this low-dimensional code vector. And if the input is following the desired distribution, then the difference between the input and output would be pretty small. Otherwise, if the input doesn't follow the training data's distribution, like abnormal data appeared in the input, the reconstruction error will be high, because in the training data, it does not look like this. So it cannot reconstruct a abnormal input data. Therefore, the reconstruction will be high. But if the input image follow the normal distribution, which has a lot of such images in the training data, the autoencoder will be able to reconstruct the output. So the reconstruction error will be low for normal data and will be high for normal data. So we can use such autoencoder to deal with many different signals, including images and also sound and the audios. So here's a demo to detect the anomaly detection for the fans. So we purchased the fan, and here we have a microcontroller attached to the fan, which has 256 kilobyte of SRAM, only 1 megabyte of flash, only 64 megahertz. And we apply anomaly detection here. And when we are picking the fan using a screwdriver, and we can see later the light is going to change the color. Yellow light is going to light up right here as we poke the fan, creating some noise. And after a while, the yellow light will disappear. And if we shake it, the yellow light will appear again, since we have a gyroscope, a accelerometer in the fan. You shake it, it will light up, the yellow light will light up. It's pretty small. Okay, so this is the summary of today's lecture. We introduced the TinyML concepts and the challenges of TinyML, and also how do we design the models that can fit tiny devices and apply them to our daily lives, including vision tasks, audio tasks, and also time series tasks. And finally, let's see some of the demos in our AITA, which introduced in the last lecture, and let's see some of the demos. So the website is actually miti.study, and it's catered for our course. So we can ask some questions like, if you're not clear of some concepts, like how to perform model distillation, which we learned in the last lecture. We are using the RAG technique to do the embedding of our lecture slides, lecture notes, and also lecture videos. And we concatenate the question with our prompt and feed it to the large language model. And then it can give us a very detailed answer. And what I like about it is you can actually click the link to watch the corresponding lecture video. You can also click the corresponding link to find the textbook which describe this particular concept. What is interesting is actually you can test yourself by creating quizzes. For example, create a quiz about neural network tuning. And let's see what it creates. What is the primary goal of neural network pruning? Increase the model size, reduce the model's computational complexity, enhance the model's accuracy, increase the number of neurons. Seems pretty simple, huh? We can also ask you some complicated concepts, like how to, maybe you guys can ask a question. Some question you want to ask in Piazza, let's try it here. Somebody want to give it a shot? If the activation is larger than the patch size. How to perform patch patch-based inference with the object is larger than what? Then the input is larger than the patch size. Doesn't quite make sense. You mean the object is larger than the patch size? Oh, then maybe one object will be across two different patches. That's your question, right? Okay, I got it. Okay, let's see. How to perform patch-based inference if the object is larger than the patch size? Divide the input image into smaller, manageable patches. Each patch is processed separately through the model. This reduces memory consumption and allows inference on devices with limited resources, such as microcontrollers. We talk about receptive field distribution. That's exactly what we discussed. Overlap handling, that's the general methods, and finally do neural architecture search. I think this is very general, but I didn't solve you a very specific question in this case. I would give it a vote down because it's not specific. Okay. All right. So that's maybe one candidate for you to think about for final projects. Building something like this will be very doable for the final project. And feel free to ask the AITA, but we are always here to help you. So consider us as the final source of help. Okay. All right. That's all for today's lecture. Thank you.